Isomers and the arrangements of atoms in space. This is chapter 4, and I highly recommend that you have access to your model kits for this chapter. Build the molecule, look at how it's arranged in space. Don't just trust the three-dimensional images drawn on the slide. Okay. Isomers. There are many different types of isomers, and so there's a lot of vocabulary to learn for this chapter. Isomers are compounds that have the same molecular formula, but maybe different structures. So different types of isomers include constitutional isomers, where we have the same molecular formula, but a different connectivity. And then there are stereoisomers that have the same connectivities, but different spatial arrangements. Now, within the idea of different spatial arrangements, we have conformational isomers that are the result of simple rotation about single bonds or rotation from the shifting of a single bond in an amine. So amines have their own special category, and we're not going to worry about that. In fact, we hardly ever talk about amine inversion. But then we have what we call stereoisomers that have the different spatial arrangements, but it's more than just a difference in single bond rotation. They have different spatial arrangement because they are configurational isomers. And configurational isomers can be separated chemically, while conformational isomers that are the result mainly of rotation about carbon-carbon single bonds cannot be separated chemically because rotation about a carbon-carbon single bond does not result in a different molecule. But if we have configurational isomers, these can be separated because they are, even though they have the same molecular formula and the same connectivities, the difference in their spatial arrangements is such that they are physically different molecules with at least one different physical property. Okay, and so the first type that we're going to talk about are SIS Trans Isomers and EZ isomers, and then we're going to talk about isomers that contain asymmetric centers. And we have several definitions for an asymmetric center, and we have several vocabulary words that mean asymmetric center. And so you should get out a piece of paper to keep a list of all these vocab words. Oh, that's not good. For constitutional isomers, these isomers are physically differing in the way the atoms are connected. Okay, so we can compare several different sets of constitutional isomers on this slide that shows how we have the same atoms, but they have a physically different connectivity. For example, ethanol versus methoxymethane. So we have an ether where we have carbon bonded to oxygen, bonded to hydrogen, and then we have methoxymethane that is a carbon bonded to oxygen, which is then bonded to carbon. They both have the formula C2H6O1. C2H6O1, but they have a physically different connection between the atoms. And so that is a constitutional isomer. The other constitutional isomers provided are, for example, different location for a chlorine. Chlorine is located at a different atom. So 1-chlorobutane versus 2-chlorobutane. They have the same chemical formula, but the chlorine is connected at a different position of the butane. And then we have pentane and 2-methylbutane. So moving a carbon in the chain of pentane to, like if I took carbon 1 of pentane, broke it off, and bonded it to that creates butane, and then I bond it to carbon 2 of the butane. So they both have 5 carbons. They both have the formula C5H12, but they have different connections in how they are bonded to each other. Pentane has only primary and secondary carbons. 2-methylbutane has primary, secondary, and tertiary, and 1 tertiary carbon. Okay. Another difference that we can have for constitutional isomers would be the difference between acetone and propanol. They both have the molecular formula C3H6O. C3H6O. But an acetone is a ketone, so the double bond to oxygen has to be at a carbon that is not at the terminal carbon in a chain. While propanol is an aldehyde, and so the oxygen must be connected to a terminal carbon in the chain. So they are physically connected in a different way. That's the definition of a constitutional isomer. Same molecular formula, different connectivity. This chapter is going to focus on configurational isomers in the forms of SIS Trans Isomers of cycles, SIS Trans and EZ isomers of double bonds, and asymmetric stereoisomers for sp3 carbons. So, beginning with SIS Trans Isomers. SIS Trans isomers result from restricted rotation about a bond. There are 2 ways in which we can encounter bonds that have restricted rotation. Rings restrict rotation. You cannot rotate a single bond in a ring by 360 degrees. And double bonds restrict rotation. So for cyclic structures with restricted rotation, one of the ways in which we can denote when we can define a cycle as having a cis or trans isomers when there are 2 substituents. All right, so the cis trans designation is dependent on there being 2 substituents. If there are more than 2 substituents, then we can't use the cis trans designation any longer. Okay, for rings, the 2 substituents do not have to be identical. That is going to differ for double bonds. Okay, so for rings, as long as we have 2 different substituents, whether it is called cis or trans is going to depend on what side of the ring it is on. So if the carbons are sitting flat in the plane of the page, then the substituents that are bonded on solid wedges are essentially sticking out of the page at you. And if the substituent is on a dashed wedge, as the OH group in the trans 4-methylcyclohexanol molecule at the top right, you see that OH is on what we call a hatched or dash wedge. You'll hear me refer to it as a hatched wedge very often from here forth. That wedge is going behind the plane of the page. You can have a cis isomer that is either on solid or hatched wedges. It's simply how is the ring oriented in space. If you take the cis 4-methylcyclohexanol and physically flip it over in your brain, then the wedges will be going back. And when I flip it over, the methyl group will now be on the side, and the OH group will be on this side. So we flipped it over in space. Now they're both on hatched wedges and pointing back, but it's physically the same structure. It's still cis 4-methylcyclohexanol because the all we did was physically turn it over. And what I'm demonstrating is the difference between the wedge types. When the wedges are coming out towards you, they're solid. When the wedges are hashed or hatched, they're going back into the plane of the page. Okay? So for the trans on a ring, what you will see is that one substituent will have a solid wedge and the other will have a hatched wedge. Now these are cyclohexanes, so they could also show you this by drawing a chair. Or sometimes, and very often on exams, they'll give you a chair rather than a nice ring like this with wedges. One of the things that you can do with a chair is convert it into a ring like this with wedges, just so that you don't have to look at the chair and think about its spatial arrangement. Okay? So you can decide what is easier to look at. Hold on. I'm going to draw the chair. And then we can compare which of the two is easier to look at, the wedges or the chair. You should be able to interpret both. So you can see I've drawn the chair structure of the cis-4-methylcyclohexane. And in this case, one of the groups will be axial and one of them will be equatorial. Since methyl is bigger than the hydroxyl group, I put the methyl group equatorial. So, but if you ask me, it's easier to look at the cyclohexane drawn as a hexagon with the solid wedges. You should still be able to draw and interpret both. Okay. Other examples of cis rings, we have cis-1 bromo 3-chlorocyclobutane showing two solid wedges. So two substituents on the same wedge type, we're going to have a cis configuration. If we have two substituents on different wedge types, then it's going to be trans. So a solid wedge with another substituent on a hatched wedge, that is trans. And as we learned in lab today, cis isomers are always going to be superimposable as long as the two cis isomers will be superimposable, but they will only be superimposable if the two substituents are identical. Remember when we looked at the 1,2, the 1-bromo-2-chlorocyclopropane, and it had 0 rotational axes and 0 mirror planes. So if we don't have our two substituents identical, then we have 0 mirror planes, which means we have no superimposable mirror image. If the two substituents were the same, then we would have a superimposable mirror image. Okay? I have to think about that. That may be wrong. If I draw this, there is a mirror plane, so cis always has one mirror plane. Yep. Cis isomers always have one mirror plane because you can draw a mirror plane cutting the atoms in half. So cis isomers are always superimposable. Trans isomers are only superimposable if the substituents are identical. And they may not be superimposable even if the substituents are identical. It depends on the orientation in space. You'd have to build the molecule to see. Okay, so cis substituents are on the same side, trans substituents are on the opposite side. Here is, now we can talk about cis and trans isomers in terms of double bonds that have restricted rotation. The only way that if the double bond rotates, it breaks the pi bond, which is not favorable. And so the pi bond restricts the bond from being able to rotate. And this results in cis and trans isomers because the proximity of groups on the carbons are fixed in space, and that means that the isomers cannot be superimposed on one another. So cis isomers have two identical substituents, in this case hydrogens, that are on the same side of the double bond. And trans isomers have two identical substituents, in this case hydrogens, that are on opposite sides of the double bond. Now, you can see a terminology here written in green that says vinylic. This is a very important term, and it's going to be used throughout the semester. And what vinylic is describing, a vinylic carbon is a double bond carbon. And a hydrogen bonded to a vinylic carbon is called a vinylic hydrogen. So the double bond carbon is a vinylic carbon, and the hydrogen bonded to the vinylic carbon is a vinylic hydrogen. Okay? And if we describe two groups as being vinylic, we are saying that those groups are on different carbons. Not the same carbon, different carbons. But both carbons must be double bond carbons. So these two hydrogens are vinylic, not only because they're bonded to a double bond carbon, but because they are not bonded to the same carbon. Okay, and you can see this is the cis isomer in condensed form, and we've also drawn the cis isomer in a skeletal structure. And here we have the trans isomer and the trans isomer as a skeletal structure. So cis trans isomers have different physical properties. Cis isomers that have identical substituents, so two hydrogens and two methyl groups. Each vinyl carbon has the same groups. The cis isomer will have a dipole, but the trans isomer will not, because the dipoles cancel. Notice that the arrows are pointing in the same direction, but opposite direction. They are on the same angle, but in opposite directions. So it's like saying, I'm adding this one and then I'm subtracting the exact same value. That equals to 0. So that's the double bond. The isomers have different boiling points and different dipole moments. For cis-trans rings, we have different boiling points. And the cis isomer is more sterically hindered because the methyl groups are on the same side of the ring. And the trans isomer is less sterically hindered because the carbons are spaced further apart when they're on opposite sides of the ring. So now we can look at some more terminology. If we have two identical groups, but they are bonded to the same vinyl carbon, then we cannot have cis-trans isomerism. To have a cis-trans isomer, the identical substituents must be on different carbons. So the groups that are the same atom or group of atoms must not be bonded to the same carbon. If they are bonded to the same carbon, that is called geminal. A geminal groups are two groups that are bonded to the same carbon. So these hydrogens are on the chloropropene. The 2-chloropropene are on our geminal hydrogens, and the methyl groups on the molecule at the right are geminal methyl groups. And so geminal and vinyl are ways in which are terms that are used to describe where groups are located in a molecule. Okay, so talking about different conformations, we've talked about going back to our chart, talking about stereoisomers and different spatial arrangements, configurational isomers, and we covered SIS Trans Isomers, and now we're going to cover isomers that contain asymmetric centers. I will start that in the next video.